What's up guys, welcome to this R session. So today's session is just a quick diversion into fitting neural networks using the neuralnet package in R. I will be covering the help documentation for the neuralnet function in the neuralnet package, so you probably don't need to go through all of the documentation. But what you might want to do is revisit the lecture where we covered the iris data and constructed a response curve. That might be relevant for today's lecture. In any case, I would like to note that even though I do have some issues with this particular package as it pertains to fitting neural networks, I think I did actually moan about some of the issues in the lecture, and I will mention it again as we move on to other packages. It is still a useful package to learn. Firstly, because, well, it's probably the easiest interface to learn. If you're coming from the regression context in R, the sort of model formula interface is preserved, and that's nice. Two, the parameter names for the functions are such that you'll see familiar jargon from the theory, I guess, which is nice. And you get to plot your neural network, which I guess is cool if you like the directed graph. In any case, that's that. Let's jump in. What's up guys? So for today's example, we're going to be looking at the iris data again. Our goal is to analyze the iris data using the neuralnet package. No validation, just use all of the data. So we're not going to be worried about the learning paradigm just yet. And then evaluate the response curve under a neural network. Okay, so really this is all just about getting to know the neuralnet package, fitting our first neural network. And yeah. Okay, so as you'll see from the template file, I've already called in the neuralnet package. And then we've got a bunch of tasks ahead of us. Task number 0, and this is task 0 because this is just general good practice when working with neural networks, and that is to prepare the data by scaling the inputs of the iris data. Okay, now before we do that, it's probably worth discussing why we'd want to do that. Well, as it happens in the context of neural networks and I guess regression problems in general, throughout the nodes on your neural network, all of the weight parameters will be dependent on the scale of their respective inputs. Okay, so if you think about it, on your neural network, on the initial hidden layer, okay, all of those weights will be dependent on the scale of the input data. Okay, so what does that mean? Well, that means that if you have certain inputs, say, varying across orders of magnitude, say, one of your columns takes on very large values, then that's actually detrimental for the learning algorithm which you apply. So what is the learning algorithm again? Well, we've got some numerical procedure which trains the parameters of the network based on some objective function. Okay, and in the context of neural networks, that's typically gradient descent through backpropagation, so it needs to calculate the gradients of the weights throughout that neural network. Okay. Now think again about that initial hidden layer. You give your learning algorithm some starting values. Let's say you have one column with really large values. What's going to happen? Well, everywhere throughout those nodes, they're going to saturate. The gradients are going to be tiny. So to start out with, your networks or your optimization return is going to be in a bad position to try and find a level minimum. Okay, so the long and short of it is, theoretically, it's not that important, but because we live in a numerical world, we actually need to evaluate these things numerically. It's good for our learning algorithm to scale the inputs first. Okay, so that's what we're going to do. And the way we're going to do it is as follows. This is going to be a simple form of scaling. Okay, I'm going to create a new data frame, okay, which is first just going to be a copy of the iris data. Okay, I'm just going to rerun everything. Okay, so let's just go head iris. I just want to show you that they are the same. Okay, so head iris and then new data. Okay, so you can see for now they are the same. Okay, and then what we're going to do is we're going to take this new data, dollar sepal length, and we're going to go scale each one of them. So new data dollar sepal length. Okay, so that's going to scale the first input. Okay, and what does a scale function do? Well, you can go check it out. Scale. Okay, question mark scale. Well, you give it some data, it says center, and then scale. What does that mean? It subtracts the mean and divides by the standard deviation. Okay, and we're going to do that for all of our variables. Okay, so let's go the next one. So sepal width is probably going to be the next one. Yes, sepal width. Okay, and then we're going to go petal width. And then we're also going to scale petal length, right? So okay, so this is the simplest form of scaling we can do. There are other ways to scale as well. Today we're going to do this. Okay, so let's have a look at what the effect of that was. New data, first it was the same, then we're going to scale it. Let's just say sepal length. Okay, let's scale everything. Okay, and now let's go call head new data again. And as you can see, what's it done? Well, it's scaled these inputs, so they'll run over different ranges now, but they'll be on some orders of magnitude, typically between like -3 and 3 if you scale it in this way, unless you have some really outlying observations, that kind of thing. Okay, but again, there are other ways to scale. This is the simplest form. We're just going to apply this here. Okay, and everything we do from now on is going to be in terms of this new data frame. Okay, cool. So let's move on to the analysis. Task 1, fit a 5 network to the iris data using the petal predictors. Okay, so we're only going to use 2 of the predictors. Choose an appropriate specification for the activation and objective functions. And set the parameters for the backprop algorithm. Plot the resulting model object. Okay, so cool, we're just going to fit a model. We're going to take the output from that model, put it in an object called res, and the function we're going to use is obviously neuralnet. Okay, so let's have a quick look at what is in the function neuralnet. Okay. Neuralnet, so question mark, neuralnet, what does it do? Okay, so training of neural nets, obviously. Description, train neural networks using backpropagation, resilient backpropagation, so RProp, with or without weight backtracking, so there are 2 variants of that, or the modified globally convergent algorithm, there's another algorithm. The function allows flexible settings through custom choice of error and activation functions. Cool, we want to do that. Furthermore, the calculation of generalized weights, we're not going to be worried about that because we're going to be moving on from this package later. Okay, so let's look at the function and its usage. So neuralnet takes as input formula, which is a symbolic description of the model to be fitted. Takes data, a data frame, so as usual. Hidden, a vector of integers specifying the number of hidden neurons or vertices in each layer. Okay, cool. So those are sort of dimension specifications, right? We can specify how many layers by just concatenating the number of nodes in a given in each layer, and those just pertain to the hidden layers. Why don't we determine the input and output dimensions? Well, that's typically determined by the problem we're working on, right? So here for example, we've got 4 inputs. Our output is species. It's going to have 3 categories, so maybe we'll encode it, hot encode it so that it has 3 outputs on the output layer. Okay, and that's determined by your data. And we get to specify the dimensions of the network in terms of the hidden layers. Okay, next parameter, threshold, a numerical value specifying the threshold for the partial derivatives of the error function as stopping criterion. Okay, so remember, we've got a numerical procedure which fits the model to the data. Here it's going to be gradient descent. Okay, that means calculating the gradients of our neural network with respect to some objective function through backpropagation. We'll pick the particular backpropagation algorithm, and this is the threshold below which we need all the gradients to fall before we say that, okay, our gradient descent algorithm has converged. Okay, so this is a stopping criterion for our numerical procedure. Step max, the maximum number of steps for the training of the neural network. Reaching this maximum leads to a stop of the neural network's training process. Okay, Cool. So again, stopping criterion. Rep, the number of repetitions of the neural network's training. We're not going to worry about that. It's going to be set to 1. Start weights, so a vector of starting values for the weights. You could specify that if you want. We're just going to leave it as is. So set to null for random initialization, which we'll leave. Learning rate limit, so a vector of lists pertaining to lowest and highest limit. So this only pertains to rprop and grprop. We're not going to be worrying about that. Learning rate, a numerical value specifying the learning rate used by traditional backpropagation, used only for traditional backpropagation. Okay, so you'll see there when we specify the algorithm, when we specify it to be backprop, then only can we set the learning rate. And that's what we'll do for today's example. Just some other parameters. Lifesign is a string specifying how much the function will print during the calculation of the neural network, because that means during the backpropagation or gradient descent algorithm, while it's optimizing it, it'll report certain statistics, how it's faring, and we'll set that as well. Lifesign step, an integer specifying the step size to print the minimal threshold in full length, in full lifesign mode. Okay, so that is if you specify a particular reporting, how often should it report? So say once every 10,000 steps or 1,000 steps or whatever. Algorithm, so a string containing the algorithm type to calculate the neural network. The following types are possible. Backprop, so that's a traditional backprop algorithm they're referring to. Rprop plus, rprop minus, SAG, or SLR. Backprop refers to backpropagation, and rprop plus and rprop minus refer to resilient backpropagation, blah, blah, blah. So the default here, you can actually go check up here, is just rprop plus. For today's example, we'll use traditional backpropagation. Okay. Then some other things. Error FCT, a differentiable function which is used for the calculation of the error. Okay, so that's the error function, the objective which we need to set, and we need to pick that depending on what problem we're working on. So we can either write a function for that, or we can use the default. So it says alternatively the strings SSE and CE, which stand for the sum of squared errors, and the cross entropy error can be used. So in a regression problem, what do we use? SSE. In a classification problem, CE, cross entropy error. ACTFCT, activation function. A differentiable function which is used for smoothing the result of the cross product. These are just the activation functions. Okay. You can specify 2 types as defaults, and that is logistic or tanh. Otherwise, you can specify your own. Okay. So for today's problem, we'll be using logistic. Okay. And then remember, you don't want on the output layer to incorrectly specify the activation function. Okay, so, and indeed, that's what the next parameter is for, linear.output. Okay, so this is a logical value, which says if the activation function should be applied to the output neurons. So they're either set to linear, or they are set to whatever the activation function which is specified. So if you're in a classification setting, what you want to do is you want to set the logistic function to be the activation function throughout the network, including the output layer. Whereas when you're in a regression setting, you might want the activation function to be logistic everywhere except on the output function, on the output layer. So then you set linear output equals true. Okay, and just be careful. Let's see what the default is. Linear output equals true is the default. So if in the classification setting, we need to set it to false. Okay, and that's that for the parameters. Let's head to our function and start fitting our neural network. Okay, cool. Task 1, fit a neural network. Okay, so what I'm going to do is I'm just going to set a seed for now, so 2021, and then we go res. This is just so that you get the same or similar result to me. I believe it'll be the same result if we do it this way, because there's going to be random weight initialization and an algorithm which optimizes, obviously. Okay, so res equals neuralnet. We're going to model species as a function of petal length plus petal dot width. Okay, so we're only going to be using the petal predictors. We need to specify a data frame, and be careful for neural net, you always need to specify a data frame. And the one we're going to give it is new data. Why? Because that's the scale data. Cool. Then what do we specify next? For the 5 network, okay, we need to specify the dimensions. Okay, so I'm going to do this on a new line. Okay, so we're going to go hidden equals C equals 5 equals C5. Yes. Okay, so we've got 5 nodes on one hidden layer. If this was a 5-2 network, then it would have been 5 nodes on the first hidden layer, 2 nodes on the next hidden layer, so on and so forth. Okay, but here we are tasked with specifying a 5 network. Choose an appropriate specification for the activation and objective function. So what was that? That was going to be activation function. This is the classification problem, so we want it to be logistic everywhere. The objective function, so in this case error FCT is going to be cross entropy error. And then linear dot output equals false. Why do we want to say that? Because we don't want it to have linear inputs on the, or linear outputs go into our cross entropy error function. Okay. Cool. Linear output equals false. What else is there to determine? Okay, so that's it for the activation and objective functions, and set the parameters for the backprop algorithm. Okay, so first we maybe want to specify that we want to use the backprop algorithm. So we're going to set algorithm equals to backprop, not backprop. Algorithm equals backprop step max. So we're going to set the stopping criterion to be run 1,000,000 steps before you give up on looking for a minimum. So 10 to the power 6. We're going to set the learning rate because we can set the learning rate if we use back propagation and make that 0.05. We're going to set the threshold to be 0.01. Okay, so that's the level below which all the gradients for the weights have to drop. We can go life sign equals full. And then we've already specified everything else. Okay, so that's that for now. So what's life sign equals full gonna do? Just so we know, life sign, okay, the options are none, minimal, or full. If we set it to full, it's gonna keep reporting as we go. As it's fitting the neural network. Okay, so let's see if this runs. I'm just going to rerun everything. Okay, and there you go. So it starts out, okay, with a neural network with 5 nodes and 1 hidden layer. Threshold parameters set there. It's got 1 repetition, and here are the steps of our algorithm. So at the 1000th step, it said, okay, the min observed threshold, or I guess max amongst the gradients would have been 0.078, okay, and that's not below the threshold of 0.01. Okay, and then every 1000 steps it actually reports a value. You can see it sort of dropping, and then at the 20,747th step, it satisfied the stopping criterion, and this is the error it produces on that particular objective function, the cross entropy error, and it took 2.39 seconds to run. Okay, cool. So that's it. That's fitting our neural network. Okay, so what's next? Oh, plot the resulting model object. Okay, so let's plot that, because what's cool about this package, it allows you to plot your neural network. So it gives you that nice directed graph that I was moaning about, shows you what the structure of the neural network is that it fitted. Okay, and as you can see here, like we said, take 2 inputs, petal length, petal width, and try and predict which species it is. So it would have 1 hot encoded things here. So if a species was Setosa, it will be 100. If it was versicolor, it will be 010. Virginica 001. Okay, and then obviously we specified a single hidden layer with 5 nodes. So one hidden layer in the middle here, 5 nodes on that. And then what this graph has reported is shows you actually what the particular weight values are that it estimated using your gradient descent algorithm. Okay, so after 20,747 iterations of this particular gradient descent algorithm, for the particular starting values that you set using the seed, you get an error of 8.22 something. Okay, cool. So that's the structure of the neural network. Looks cool, but not necessarily easy to see what the neural network is doing. Okay, so what I'm going to do is I'm just going to comment that out, close this window. Okay, and then what we're going to do is, right, we're going to go on to task 2, and that is to construct a response curve for the model fitted in task 1. Remember that the data are now scaled. Okay, so because we fitted our model on the scaled data, okay, we need to now pass this scaled range when we create our lattice on which we want to predict for our response curve. Okay, so what does that mean? How did we construct our response curve again? Well, we created regularly spaced data points along each dimension, along each input dimension. We repeated them in an appropriate way to get regularly spaced coordinates in the joint dimensions. So yeah, same thing as we did last time. We're going to create a sequence running from the minimum of the observed. So new data, which was the first one. It's going to be petal width to the maximum of on the new data. Petal width, and we want to create a sequence of length equals m, and we set m equal to be 100. Okay, next one we're going to go from the minimum of new data, petal width, petal length to the max of new data, petal length equals m. Okay, so those are regularly spaced coordinates. We're going to repeat them in the appropriate way. And then we want to create a lattice structure. What does that mean? Well, we've got a lattice that we want to pass to a prediction function. So we need to give it a data frame with the appropriate names. So that means petal width is going to be equal to x1, the repeated coordinates. And then petal length is going to be x2, the repeated coordinates for x2. Okay, and then we want to evaluate a prediction. So if we go back to our help file, you'll see that one of the functions you're going to have a look at is, okay, plot.nn we looked at, predict.nn can also look like at, that's again just predict, give it an object of class neural net, give it some new data, and yeah, then it'll construct some predictions. So go predict, use the model that we fitted, which was res, and then pass to it now the lattice, right? Because we want to predict at the coordinates on this lattice. Cool. Let's run that. See if it worked. And then what does pred look like? Pred is going to be a matrix, right? So let's look at that. Okay, and then what we want to do is we want to extract the maximum from each of these rows as our prediction for the particular class. Okay, cool. So how do we do that? Go and apply to pred along which dimension? Along the first dimension, which is each row, which dot max. Okay, and that's going to give us the predicted class. Okay, so 1, 2, whatever. And now what we're going to do is we're going to plot our regularly spaced coordinates and we're going to assign a color to each of those coordinates according to which class the actual observation is, or the predicted observation is. Okay, and the colors we've picked, our palette's going to be blue, gray, and purple again. So what are we going to do now? We're going to plot our lattice, so petal length as a function of lat $petal width. We're going to say plotting character equals 16. Color of each of those is going to be picked from our color palette, so colors, CLSS, which is the predicted classes. Right, so have we evaluated predictors? Yes, we've class, colors, plots. And there we go. Okay, now sort of interpret what's going on here. Let's overlay the data again. So remember, this is now going to be the new data, the scale data. Petal length, so new data.petal length as a function of new data $petal width. Okay, and then we want the labels that we print there to be as equals as numeric new data species. Cool. Now what's that going to do? That's just going to write a number corresponding to what species it is in the appropriate coordinate position at which we observed it. Okay. And there you go. Okay, so that's our original data. Okay, so I've got first species here, second species somewhere in the middle here, and then our third species up top here. And then what is this in the background? This is going to be our response curve for our neural network. So what is our neural network doing? Okay, well, it's partitioning this feature space, but it's partitioning it using these nonlinear bounds. And what's interesting about these nonlinear bounds, okay, so this one is sort of semi-linear, because it's just splitting the data here sort of halfway between. But what's happening with the 2s and 3s here? Okay, so it's almost like it's sort of reaching, trying to get around the data here to sort of optimize, right? And remember, what does it want to do? According to our objective, it wants to classify all of these correctly, so it has to create this nonlinear bound, trying to avoid all the 3s there to get around there. Okay, so that's one way to think about what's going on here. Okay, cool. So that's fitting to data. Just one thing I would like to note here, and this is a particular issue with this package, is that what we've actually predicted here, or I guess let me go back to this step. Right, so let's go to the predictions that we've constructed here. So I say let's create a prediction matrix based on the input coordinates from our lattice. Okay, so we get this matrix out. Ideally, what we would have wanted is for these to be probabilities. Now for this package, it seems that those are not actually probabilities in the sense that they do not add to 1. And even if you set type equals to probability, it doesn't actually set it to 1. So let me show you what that means. So the row sums on pred don't actually add to 1. Okay, so on the output layers of our neural network, okay, what we ideally wanted to do is we wanted that the output activations to actually behave like a distribution. So here they don't quite actually behave like a distribution. Why? Because we're constrained to setting the activation function to logistic. So yeah, that's not ideal because, well, the logistic outputs on that output layer need not necessarily add to 1. Okay. So this is one of the issues I actually see with this package, which means it's probably not ideal for general purpose application. It's a bit of a strange one. I guess you could specify your own activation function, but then it applies throughout the whole network. So yeah, it's not clear to me how you actually get around to fixing that. But nevertheless, it seems like it's sort of close enough to rock and roll that it'll actually work. I think it's a bit dubious, but yeah, that's not the biggest problem. Okay, now the biggest problem with what we've done so far is, okay, I've said take all the data, fit a neural network to the data, just go for it, okay? Now, that's less than half the story, as you should know by now. Why? Because, well, the neural network is just a model. Yes, we can fit a model to the data, but that does not mean it's commensurate with learning, okay? We haven't actually applied any complexity controls to the data or to the model here, so we cannot guarantee that it is actually learned, okay? And that'll be the topic of our next video. See you in the next one.